Welcome to the Deep Dive.
Hello.
Today, we're tackling a big one. How do scientists actually know the universe is 13.8 billion years old?
Yeah, it's a number we hear a lot, but the how is fascinating. We're looking at the source, measuring the universe's age today.
Right, and our mission really is to unpack that science, make it clear how they got there. It's not just a guess, is it?
Not at all. So, a key starting point is light itself.
Like, how so?
Well, light travels at a finite speed, a very fast speed, but finite. So when we observe a galaxy that's, say, millions of light years away.
We're seeing light that left it millions of years ago.
Exactly. We're literally looking back in time. The further away we look, the further back in time we see.
Okay, so distance equals time travel in a way.
Mm.
How does that get us to the start, though? To the Big Bang?
Oh, you combine that with the fact the universe is expanding. We see galaxies moving away from us, and the further they are, the faster they seem to recede.
Ah, right, the expansion. So you can sort of run the clock backwards.
Precisely. If things are moving apart now, they must have been closer together in the past. You trace it all back to an incredibly dense, hot state.
The Big Bang itself. But that's based on observation, right? There must be other evidence.
Oh, absolutely. A huge piece of the puzzle is the cosmic microwave background radiation, the CMB.
The CMB. I've heard it called the afterglow of the Big Bang.
That's a great way to put it. Think about the universe maybe 380,000 years after the beginning. It cooled down just enough for atoms to form and, crucially, for light to travel freely without just scattering off electrons.
So before that, it was like a dense fog.
Kind of, yeah, an opaque plasma. The CMB is basically the light from the moment that fog cleared. It's been traveling ever since, stretching out as the universe expanded, cooling down into the microwave range we detect today.
Wow. So it's like a snapshot of the universe when it was just a baby.
Exactly. A baby picture imprinted on the entire sky. And we've taken some very detailed pictures of it.
How do we do that? Up close.
Well, not up close. With incredibly sensitive satellites like WMAP and more recently the Planck satellite.
And what do they show? Just a uniform glow.
Almost uniform, but not quite. They map tiny, tiny variations in temperature across the CMB, like minuscule differences.
And those little fluctuations matter.
Hugely. They're the seeds, the slightly denser spots in the early universe that, gravity could grab onto. These eventually grew into the galaxies and galaxy clusters we see today.
Okay, I think I get it. The pattern of those hot and cold spots in the CMB tells us something fundamental about the early universe.
It tells us a lot. By analyzing the size and distribution of those spots, scientists can calculate key properties of the universe, including its overall geometry, how much dark matter and dark energy there is, and critically for our question, its expansion rate.
The Hubble constant again.
Exactly. The CMB gives us a very precise measurement of the Hubble constant from the early universe. And knowing that rate lets you calculate the time back to the Big Bang.
So that's where the 13.8 billion years largely comes from.
It's a cornerstone, definitely. But what makes the case so strong is that it's not just the CMB.
Ah, okay. What else?
Well, scientists also measure the ages of the oldest known stars, particularly those in globular clusters. They use totally different methods based on how stars evolve, how they burn their fuel.
And what do they find?
They find the oldest stars are, well, nearly as old as the age derived from the CMB, maybe around 13 billion years or so. They can't be older than the universe itself.
Right, that makes perfect sense. It's like an independent check.
It is. And then you also look at the large-scale structure of the universe, how galaxies are distributed in huge filaments and voids. Those structures took time to form via gravity, and the timescale fits.
And the expansion rate measured more locally from
Yeah.
supernovae and things.
Yes, measuring the expansion rate today using different techniques provides another piece. There's some tension currently between the early universe measurement from CMB and the late universe measurements, but they are broadly consistent within this age framework.
So it's really a convergence. It's the CMB, the oldest stars, the galaxy distributions, the expansion rates.
And even the relative amounts of light elements like hydrogen and helium created just after the Big Bang, all these different lines of evidence using different physics and observations point towards that 13.8 billion year figure.
It's not just one calculation. It's like this whole web of evidence. Light, physics, deep time detective work, as the source puts it.
That sums it up nicely. It's a remarkably consistent picture built over decades.
So to quickly recap, looking back in time via light travel and analyzing the Big Bang's afterglow, the CMB. These, combined with other data, give us that solid age.
That's the essence of it, a robust conclusion from multiple independent lines of scientific inquiry.
It's quite something to think that when you look up at the night sky, you're not just seeing space, but deep time. Makes you wonder, doesn't it? What else will we uncover as we look even deeper, even further back?
Indeed. The story's likely not finished yet.
A great thought to end on. Thanks for this fascinating deep dive.